an exercise rather than something that would be given explicitly in the exam question, but it's very, very important. If you can't write things with second derivatives as two first orders, you're heading for zeros or close to it in questions with a second derivative. Okay, so the first thing to do in every case is to let your first derivative, in this case y dashed of x, equal to some other variable, say v. Okay, now we could also written dy dx. And then what you do is you differentiate both of these with respect to x, or maybe with respect to t, depending on context. And here you're getting the second derivative of x is equal to the first derivative of v. We might just write down v dash. We could do dv dx. As level 8, you should be comfortable with both. And this means you can rewrite the above equation, a differential equation, in terms of v. So you got a second derivative, that's v prime, plus y dash squared. Now y dash is the same as v, so that's v squared, minus twice y. You don't really need the of x anymore, like y of x is just equal to y when you get down to this kind of thing, equal to 3. And what you want to get is a differential equation for y, which we actually already have, and then a differential equation for v, which comes out of this. So we're just going to add 2y, and we're going to take away v squared. Just solve it as an algebra problem. You get v dashed is equal to 3 plus 2y minus v squared. And now we can write this carefully as two first orders. So we're talking, you don't have to write it as carefully as this, but I think it's a good idea. Like if you're going off doing a Heinz method or Euler's method, this is what you should be doing. So actually don't need so much because I'm doing v dashes here. Before we've tended to use dy dx. Anyway, so y dash, the slope of y is v, and the slope of v is 3 plus 2y minus v squared. And we also want to put the initial values here. The initial y goes with this, which is 0. And look, y dashed of 0 and y dashed same as v, so you got v of 0, 0. That's the first one. The second one, we'll just probably write down the question. It got second derivative is twice the first derivative. And we have y of 0, y is equal to 0. So it says y is equal to 0 and dy dx is equal to, actually I have this on another screen, it'd be easier, 1 when x is equal to 0. So this is just another way of writing, this is y of 0 is equal to 0. When x is equal to 0, this is x, y is equal to 0. And then the other one, dy dx, well this could be, yeah, so we could write this in various, you could if you wanted, it's not terrible. Dy dx as a function of x, so when x equals 0, you get out 1. Okay, so as before, what you do is you let the first derivative, ev, now differentiate both sides with respect to x. And here we've got the second derivative of y. If you differentiate the first derivative, you get the second derivative is equal to dv dx. And now carefully write our differential equation in terms of v. So the second derivative is dv dx equal to twice the first derivative, and dy dx we've already said is v. So now we know dy dx and we know dv dx, we can write down the two initial value problems. They're like simultaneous differential equations, like systems of differential equations. And I think you can even do, like, if these things are solvable exactly, you can actually do Laplace on the two first orders. You may or may not have done something similar. Well, you wouldn't have done this exact thing with Marina, but you could actually do Laplace transforms now, I think. Just that'd be a bit of crack though. So dy dx equal to v, and dv dx is twice v, and initial value y of 0, 0, and v of 0 is 1. Okay, so that's that. The third one, again, I'll write down the answer. I'll write down the question. Second derivative of s, which is presumably displacement, is equal to 6, given dSdt is equal to 4, and s is equal to 0. So this s is not due to Laplace s when t is equal to 0. So it's just written slightly differently. So here you could write down that this means, say, here I'll flip between ds dt and s dash. So the derivative of s, ds dt, when t is equal to 0, you get 4. And the other one says that s at time 0 is 0. Okay, as after that it works the same. Let the first derivative be v, and in context s here is probably displacement and that is actually velocity. Differentiate both sides, or I guess here we're working with the dashes. Look, let's mix it up. You should really be comfortable mixing them all up. They're just different notations for the same thing. Leibniz versus Isaac Newton. So differentiate both sides with respect to t. I get the second derivative of displacement is equal to dv dt. And if I continue what I was doing above, the second derivative of displacement is equal to 6. And the second derivative of displacement is also dv dt. So I get dv dt is equal to 6. So now I'm ready to go. I have two equations, differential equations. The first one is ds dt is equal to v. And the second one is dv dt is equal to 6. Initial s is 0. Initial v is, now remember v is the derivative of s, so I'm using this, is equal to 4. And then one more. So I have, the question here is y double dashed of t is equal to twice t. Now there's a weird if there. I'm just going to pause this and correct that for next year. I'll just show it to you here. If dy dt, the if is just weird. Yeah, anyway, let's write down the rest of the question. So the second derivative is 2t, and we have dy dt is equal to 1, and y is equal to 10, and t is equal to 0. Okay, so again, this should be nearly getting boring. Let dy dt, or let's go back to the y dash of t equal to v. Differentiate both sides with respect to t, and I get y dash of t is equal to v dashed of t, and let's just call it v dashed. Writing the equation above, the second derivative of y is v dashed, and it's also equal to 2t. And now we have enough to write down our two initial value problems. The first says that y dashed is equal to v, and the second says v dashed is equal to 2t. The initial y dashed is 1. Y dashed of 0 is equal to, oh no, that's, whoa, did I make this mistake above? No, I didn't. So the y dashed is the differential equation for y. So the initial y should go here. And it says y equal to 10 when t is equal, so y of t equal to 0 is 10. And then the v of 0. Now v is y dashed, or dy dt, and the initial dy dt is 1. And we're off again. A similar question. Particle mass m, constant acceleration a0 satisfies this differential equation. Right, this has two ODEs. So again, let the first derivative, which here would be the function that we're interested in is s. So ds dt equal to v. Now to be fair, then this does be velocity. This is velocity because s is actually displacement. Differentiate both sides with respect to t, and you get that the second derivative of displacement is dv dt. And then you can go to the answer here really, but maybe we'll just be a bit more careful. and we would rewrite the equation. So we've got mass times second derivative of displacement, and that's we've just shown as dv dt is equal to mass times a0. And you want to find dv dt, you just need to divide both sides here by m. So you get dv dt is equal to a0, and I think we're pretty much ready to go. First differential equation, ds dt is equal to v. Put the initial value of s with that, it's given above, s of 0, 0. And then dv dt is equal to a constant a0, and put the initial value of v. Now, that's not given as such, but s dashed is the derivative of s. The derivative of s, the derivative of s is the same as v, so you get v of 0 is v0. That question is done. So off we go again, another example of these. So again, to do this, it's a fundamental skill. I think I wrote above that these ones wouldn't really be exam questions, but the latter two could be. Okay, so again, you take the first derivative, in this case dx dt, and set it equal to v. Now in this case, x is the displacement, so this is genuinely the velocity. If you do get the right answer at the end, now initial value problems means you must include these, but the working out you don't have to, but it's just strongly recommended. So differentiate both sides with respect to t, and you'll get the second derivative of displacement is equal to dv dt. And now your job would be to write the differential equation as much as possible in terms of v. So you get m times the second derivative of x, we've just shown, is equal to dv dt, plus lambda times dx dt. If you want to write that in terms of v, it's v, plus k. Now x of t is just x, like x is the same thing. X of t just means the displacement times t. In other words, it's just x. X equal to 0. Now your job here is to solve for dv dt. So I guess what you want to do here is maybe take away the lambda v and also take away the kx. Let's do that to both sides. You'll be left with m times dv dt is equal to minus lambda v minus kx, and then carefully divide both sides by m. So you get dv dt is equal to minus lambda v minus kx all divided by m. And maybe we'll be a little bit lazy, not that lazy, and put this answer in here. So I have dv dt. I'm previously doing dx dt first, you don't have to do that. Dx dt is v. We introduced that. The initial v should be up there is 0. I don't know why it shouldn't really be given. That's kind of poorly written question. What the hell is v? It should be x dashed of 0, 0, but of course x dashed is v. So we have v of 0, 0. And I think we had that x of, this is the wrong way around, apologies. This is the equation for v, so this takes v of 0 equal to 0. And this one takes x of 0. I think it was some parameter, little x of 0. Okay, off we go. Now, this one, the worked solution is on page 167 if you just want to see it written down. And I'll be doing calculations using Excel because I lost my calculator, so some of my rounding might be different to yours. So again, if you don't write this as two first orders, you're doing nothing right. So let the first derivative here, you're interested in x, so dx dt equal to v. You can differentiate both sides now with respect to t to get the second derivative of displacement is dv dt, and then write this thing in terms of v. So I got second derivative of x there. We just showed that that's dv dt. Plus 4 times dx dt, we've just said that that's the same as v. Plus 3 times x equals 0. It's not hard to find dv dt from there. So let's write this as two first orders. So we have dx dt is equal to v. and we have dv dt. If we take away 4v from both sides and take away 3x, and we have the initial value of x here, x of 0 is 0, and v of 0, so that'd be the initial derivative, that's given there, x dashed of 0 is 1. Okay, and we're going to point 3. Now we might just kind of explain a little bit all the variables as such that we're using. Hopefully that's enough space. So we've got time, and that goes from 0, we're actually going down to 0.3. So you want to kind of understand this table, you don't have to write it down. Tick to 0.1, tick to 0.2, tick to 0.3. We have x, we have v, and we're potentially interested in both of them, but we have an x predictor and a v predictor as well, because this is Heinz method. And if it's Heinz method, you have two predictors, one for each. The initial x is 0, the initial v is 1. The initial predictors is, it doesn't make sense. Okay, so in terms of what we're actually going to find, so we're going to find x1 predictor, v1 predictor, and that's essentially done simultaneously, and they are rough ideas of what's going on at t equal to 0.1. They're Euler predictors. They're not Euler's method because they're not jumping off the previous predictor. And then we'll use Heinz method to find x1 and v1. Then we will find, actually, if there's any shortcut, we'll take it. I don't think there are great shortcuts available anyway. So I think it's x2 predictor that we don't actually need. Now, if you can kind of cop that out, great. Otherwise, I don't think you need this either. If you calculate them, obviously it's not wrong. So from the previous t, x, and v, you're going to get x2 predictor, v2 predictor. Then you're going to get simultaneously x2 and v2. And then what you have to do is you have to find v3 predictor, and then you'll find x3. And that x3 will approximate the x value at 0.3. So this is what we're doing. Okay, so let's go, I guess. So let's start by doing two predictors. So x1 predictor is equal to the previous x. So the previous x is the initial x is 0, plus step size is 0.1 times the slope of x. Now the whole time the slope of x is v, and the slope of v is this. We're using that the whole time. So the slope of x is v, so it should be the previous v, which is 1. So you get 0.1. I won't fill in this table here. Yeah, but anyway, that's this one. And then v1 predictor is equal to the previous v, which is 1, plus step size is 0.1, and then times the slope of v. The slope of v is minus 4 times v minus 3 times x, and it should be previous slope. The previous v was 1 and the previous x was 0, so we should be able to get a number out here reasonably quickly and easily, 0.6. Okay, now we're going to go to the next step, and we're using Heinz method. So we'll have slopes divided by 2 because we're going to average two slopes. So x1, the previous x is not 0.1. The previous x, we're now looking here, remember. The previous x is 0. Now we can do the two slopes. Now I can bring in the formula. I mean, let's bring in the formula here. So just using these, I'm not really using these, but just to kind of remind you, Heinz method. So the predictor jumps off, not the predictor. There's no p there. There's no p there. That isn't there. It jumps off the previous y. And then what you do is you average two slopes, the previous slope and the predicted next slope. And the slope is given, of course, by this is the slope of x, and this is the slope of v. Okay, so anyway, x1, previous x is 0. Now we can do the division by 2 rather than doing it here. It might make more sense to do it there. And that's, I think, is what I'm going to do. So it's step size divided by 2, and then the slope of x is v. So you've got the the previous slope, which is the previous v, which is here, is 1, plus the predicted next slope, which we just found to be 0.6. Bang that into the calculator, I am getting, well, maybe we'll do the x's and the v's kind of simultaneously. So v1 is the previous v, which is 1, plus step size over 2. And now the slope of v is minus 4v minus 3x. I'm talking minus 4v minus 3x. That's the previous slope. And another one, minus 4v minus 3x. So, the previous v was 1. The previous x was 0. The predicted next v is 0.6. The predicted next x is 0.1. And we bang that into the calculator and I get, oh yeah, we said we'd do the two calculations together. So for this I get 0.08 and this I get 0.665. Okay, now we're going to, this is at, I guess, t equal to 0.1. The predictors are t equal to 0.1 as well, but they're just auxiliary calculations. Now let's go to the next level to get the next two predictors. So x2 predicted and v2 predicted. So you don't jump off the predictor, you don't jump off 0.1, you jump off the previous x, which is this 0.08. So we're talking 0.08 plus step size is 0.1 and the slope of x is v and the previous v is 0.665. And for v, the previous v is 0.665 plus step size is 0.1 and the slope of v is minus 4v minus 3x. And the previous v is 0.665 and the previous x, maybe I should start doing colors, well, not the next one, previous x was 0.08. Bang these into a calculator. This predictor for x is 0.1465 and for v I'm getting 0.375. Now you might get different things if you're around properly. I'm using Excel on the side there. So now using these we'll go to the next, we'll do our Hines method. Two Hines methods for t equal to 0.2. We're going to find x2 and we're going to find v2. So the previous x is 0.08, the previous v 0. I don't necessarily advocate doing it like this kind of parallel, but it's kind of what's happening. Step size, well, is 0.1, but you can do the divided by 2 first rather than averaging the two slopes. But you want to be clear that it's not half a step size. Really what you're doing is it's a full step size, but you're averaging two slopes. It's just kind of helps for BEMDAS and stuff like that. Now the slope of x is v. So we want the previous v, which is 0.665, plus the predicted next v, which we just calculated to be 0.375. Okay, and now for v, the slope of v is minus 4v minus 3x plus, now if I do plus minus, I did that above, it probably should be plus, minus 4v minus 3x. Okay, so the previous v and x were 0.665 and 0.08. The predicted next v we just calculated is 0.375 and the predicted next x 0.1465. We bang both of these into a calculator. The x2 is coming out as 0.132 and the v2 here is coming out at, I'll need some approximation, 42303. Okay, now we probably won't be too smart here, but I don't think we need the x2 predictor at all. No. We may, yeah, I wouldn't be too smart about it, but we actually don't need the x2 predictor. So maybe we in that case we won't be too smart about it. Let's just find the two predictors without saying anything. So the x3 predictor, I think I said 2 should be x3, and the v3 predictor. So the previous x is 0.132. The previous v is 0.42303, plus step size is 0.1, step size is 0.1. Slope of x is v, previous v is 0.42303. And the slope of v is minus 4v minus 3x. Previous v is 0.42303. Previous x, 0.132. Bang these into a calculator. This x3 predictor, which we won't actually use, just if you wanted to find the next v, you'd use it, but actually if you read the question, you just have to find the next x, and the next x only needs v predictor. So this x3 predictor is a waste of time really, but 0.17430, and then the v predictor, which we do need, 21422. And now I'll just do one more calculation. So at time equal to 0.3, let's do the next x. The next x3 is equal to the previous x, the 0.132, plus step size over 2, and 2 slopes. The previous slope, and the slope of x is v, 0.42303, plus the predicted next slope, 0.21422. And remember that division by 2 that's on the step size is actually averaging them, and this comes out to 0.16386. And if there are units, we can put them in. I'm not big on units in this. Yeah, there's meters, there's seconds, so this is a distance meters. The units on this are wrong. I'll have to change them later. Yeah, okay. So this, the meat in this question is in writing it as 2 first order initial value problems. That hint is given. There's no guarantee that such a hint would be given, but it is the first thing you want to be doing. So as we've been doing a lot, let the xdt be v, and does it say anything about displacement? But it's supposed to be. So this v actually does mean velocity. Differentiate both sides with respect to t. And you're talking the second derivative of displacement is equal to dv dt. Then you can rewrite the differential equation. So the second derivative of x we just showed is dv dt plus 2, 1 minus, now x of t is just x squared, times dx dt is v, plus x of t is just x, equal to 0, and it's not too difficult to solve for dv dt from there. So let's write down our second order initial value problem as 2 first orders. So we have dx dt is equal to v, and dv dt, just take away from both sides appropriately, you get minus 2, 1 minus x squared, and again you could write that as 2 times x squared minus 1 if you wanted, minus x. The initial value of x goes here, x of 0 is 0, and initial value of v goes here, v of 0, well, v is the derivative, so that's x dashed, and the initial value of x dashed is 1. Now this is actually a particularly easy question because it's just looking for Euler's method, and it's only going to 0.2, so it's going to be really, really quick. To show you what I mean, no predictors or anything. So txv, so you have time starts at 0 and goes from 0.1 to 0.2, and you've initial x is 0, initial v is 1, and it's just Euler's method, so there's no predictors. So this will be x1, and you'll calculate v1, and you'll need v1, and from v1 you'll get x2, and x2 is basically your answer, because x2 approximates the x value at 0.2. The v2 is actually not needed. Applicable. So this is a fairly handy question, really. Okay. So let's go. So at time equal to 0.1. So x1 is the previous x, which is the initial x, which is 0, plus step size is 0.1 times previous slope. And the slope of x we found is v, the previous v is 1. v1 is equal to the previous value of v, which is 1, plus the step size. And now the slope is a little bit complicated. Minus 2 times 1 minus x squared times v minus x. And they're all previous values. So the previous x was 0, the previous v was 1, the previous x was 0. And these are handy enough to find in a calculator. We're talking about 0.1 and 0.8. And suddenly this question is very, very quickly over because we just can find x2 now. The previous x was 0.1 plus the step size is 0.1, and the previous slope, well, the slope of x is v and the previous v is 0.8, and very, very quickly we have our answer. And I don't know if we have any units here. It doesn't say anything about units, so we can't say anything. So that was a very short exam question. I think typically, like, I could push you there to easily to 0.4 with Euler's method, or maybe to 0.3 with Hein. Off we go again. A second order, so it tells you there, you write it as two first orders. You may not be given that hint necessarily. So that doesn't say anything about x here, but it's supposed to be a damped harmonic oscillator anyway. So the v makes sense as the velocity. As we've seen a lot now, differentiate both sides with respect to t, and I get the second derivative of displacement is the first derivative of velocity. Then write my second order differential equation in terms of v. So that second derivative of x I've just shown is dv dt plus 5 times dx dt. We have defined that as equal to v, and 6x of t is just x equal to 0. And it's easy enough to solve that for dv dt, and we can write as two first orders. So I have dx dt is equal to v, and if I take away 5v and 6x, I get dv dt is equal to minus 5v minus 6x. The first one is the differential equation for x, so if you want to make an initial value, now it just says first order problems, you've done that actually, but you should just make them initial value problems. X of 0 is 0, and the initial value of v is the initial value of the derivative, which is also 0. And we're doing Hein's method here, and we're going up to 0.2, so we'll give an idea of what we're looking at here. Okay, so we do have predictors, but we're not going very far. So t, x, v, x predictor, v predictor. So the t goes from 0 to 0.1 to 0.2. The initial x is 1, the initial v is 0. These don't make any sense. So we're going to find, we just want to find what's a x2, and our x2 is our approximation of x of 0.2. If you, now we don't want to be too smart here, so maybe we shouldn't be. So what we should find first is our x1 predictor and our v1 predictor. Then we should find x1 and v1, and then we certainly want to find our v2 predictor. And in fact, that is enough to finish off the thing. The others you won't need, but we may or may not calculate them, seeing how things go. Okay, off we go. So x1 predictor, v1 predictor. So x1 predictor, the previous x, which is just initial x, which is 1. Say the previous v is the initial v, which is 0. Step size in both cases is 0.1. Slope of x we just found above is v, or we actually defined it to be v, and the previous v is 0. The derivative of v is minus 5 times v minus 6 times x. The previous v was 0, the previous x was 1. Bang these into a calculator. There's much rounding error there. I get 1 and minus 0.6. Now we're going to do Heinz method. Okay, so this is at t equal to 0.1, obviously. So we're going to have x1 equals v1 equals. So x1 is the previous x, which is not 1. Well, actually it is 1, but it's in the sense it's not this one as such, it's this one. The previous v is the initial v, which is 0. And what I'm going to do here is I'm going to I need to average two slopes, and for kind of calculation reasons it's easier to divide by 2 here. Maybe let me just say this, that a times b plus c divided by d is the same as a divided by d times b plus c. If you multiply out either, then you'll see they are actually the same. So if you want to divide two slopes, say b and c, by 2, you could also divide the step size by 2. It's basically the same thing. Now the two slopes here are the previous slope, and look up the top of the page, the slope of x is v. The previous v is actually the initial v, which is 0, plus the predicted next slope is the predicted next v, which is minus 0.6. And now things slightly more complicated for v, because the slope of v is minus 5 times v minus 6 times x. That's one of the slopes, plus the other, minus 5 times v minus 6 times x. So minus the previous v was 0, the previous x was 1, the predicted v is minus 0.6, the predicted x was 1. Bang these into a calculator. x1, I'm seeing 0.97. v1, I am seeing minus 0.45. And then, in fact, we don't actually need x2 predictor, so maybe this time I will leave it out. If in doubt, just calculate it. But we don't need it. So v2 predictor is the previous v value minus 0.45 plus step size is 0.1. The slope of v, it's up the top of the page there, minus 5 times v minus 6 times x. And the previous v I just calculated was minus 0.45, and the previous x is 0.97. Calculate that. It's looking like minus 0.807. And then I have one more calculation to go. x2, which is my approximation, is the previous x, which is 0.97, plus step size, and then averaging the two slopes using the BEMDAS. So the previous v is v1, which is minus 0.45, plus the predicted next v is minus 0.807. And I get my final answer here of there may or may not be rounding here, I'm not sure, 90715. Very good. So we're off again. Second order you need to write as two first orders. So now I know from context S is actually displacement. So its derivative is velocity. Differentiate both sides with respect to t. We are getting that the second derivative of displacement is the first derivative of velocity, and then we can rewrite this thing as twice. The second derivative of displacement we've just shown is dv dt is equal to 1, and now we've actually got the constant acceleration. dv dt is equal to a half. So fairly straightforward scenario here. ds dt is equal to v, and dv dt is equal to a half. And I think because the derivative dv dt doesn't depend on v, it doesn't make sense doing a predictor. It actually wouldn't be used. So Euler is actually going to get the answer exactly right here. Let's just make a remark. The Euler method, the error in the Euler method is order of the second derivative. Ooh. No, what I'm saying is wrong here. Heinz method would somehow get it exactly right. I don't really know how. It might confuse us a little bit, but here you've got a constant second derivative. I think here it's down here. This isn't a constant. So if this was on its own, it would get v exactly, but v it isn't. So here the second derivative of this is 0, so it'll match this very well, but the problem is it won't match the displacement exactly. It'd be interesting to kind of, like, what the formula should actually be here. Like, your S is equal to ut. Have we got u? It's actually 3t plus a half at squared. The slope here is a half at squared. And then if you put in t equal to 3 into this, so evaluate t equal to 3, I think you're seeing 9 plus a quarter of 9, which is 2.25. So you don't get the answer exactly. Heinz method would. So because Heinz method would, it would do better on the dSdt, something like that. Okay, so that's just a side remark. So anyway, the initial S is 0, and the initial V, well, V is S dashed, is 3. And we're looking to do step size of 1 to approximate S of 3. So this one shouldn't be too bad. So, so we're talking S1, it's just Euler method, V1, then S2, V2, and then finally S3. And S3 is our approximation of S of 0.3. Right, so S is the previous S plus the step size is 1 times the slope of S, which is V, and the previous V is 3. V, previous V is 3 plus step size is 1 times a half. Oh yeah, the predictor would actually come in here as such. So this looks like 3.5. And then S2, the previous S is 3 plus the step size is 1. And the slope is V, the previous V is 3.5, so you're getting 6.5. And then V2 is previous V, which is 3.5, plus step size is 1, slope of V is a half, so I'm getting 4. And then S3, previous plus step size, and the slope of S is V, and the previous V is 4, and this is where you're getting the 10.5. Now I'll just show that if you actually use, this is just a remark, I think Hein gives you the answer. So let me see. So if you, does this play any role here? So I think S1 would be, so the V1 predictor is, say, the initial V, which is 3 plus 1 times a half. Yeah, you get this 3.5. And then what would happen is S1 would be 0, step size divided by 2, and then you'll average 2 V's, the initial V and the predicted next V, and you will be more accurate like that. So whatever that would be. Am I seeing 3.25? And if you compare that with, like, S is equal to ut plus a half at squared, and you put in t equal to 1 into that, I believe you would get exactly this. Yeah, so Heinz method would get this one exactly correct. Okay, last one here again. Now this time you've got dy dx is totally abstract, so the v doesn't really stand for anything in particular. Well, I mean, it stands for the derivative, but it's not kind of its own variable. Differentiate both sides with respect to x, not t here. The second derivative is equal to dv dx. Write your differential equation in terms of v's as much as you can. The second derivative is dv dx, and you get x Now this x is like the t before, so this is a bit different to what we've seen. Plus dy dx we've just said is v. So you got dv dx, you got dy dx. Let's write down the two in first order initial value problems, and note there was no prompt. So don't expect a prompt. Dy dx is equal to v. Dv dx is equal to x plus v. So x is coming into the derivative, like time is coming into the derivative. It didn't, I think, in any of the previous actual calculations we did. Okay, the initial y is 1, and the initial v is the derivative of y, is minus 2. And it is Euler's method, but I think actually this time we might keep the table, but just to help us, because we need, because the x coming in. So the x and the step size here is 0.5. Oh, I need an extra line. .5, 1.5, and then we have y, initial y is 1, and then say v, and initial v is minus 2. Right, and we want to find y3 here, and y3 will approximate the y value 1.5. That will be our answer. Okay, off we go. So y1 equal to v1 equal to, so y1 is the previous y, which is 1, plus the step size, which is 0.5, times the slope of y, and the slope of y I've just shown is v, and the previous v is minus 2. So I think this y goes back to 0. Let's chuck it in there. And then v1, the previous v is minus 2, plus step size is 0.5, and now the slope of v is x plus v. What is the previous x? Well, we're here, so the previous x is 0, and the previous v is minus 2. Put that into the calculator, and we get minus 3. So the x is coming into it as well, so we have to be a little bit careful. So that's what's going on at x equal to 0.5. Now we're doing y2 is equal to the previous y, which is 0, plus step size is 0.5. Slope of y, it's up the top there, is v, and the previous v is minus 3. So I believe we're going back to minus 1.5. And then v2 is equal to the previous v, which is minus 3, plus the step size is 0.5. And then the slope of v is x plus v. What's the previous x? Well, we're here, so the previous x is 0.5, and the previous v is minus 3. So we'll get some number out of that, minus 4.25. So this is minus 1.5 and minus 4.25, and we're just asked to approximate y of 1.5, so we just have one more calculation to go. Previous y is minus 1.5, plus step size is 0.5, times slope of y, up the top of the page is v, and the previous v is minus 4.25, and out pops minus 3.625. And that's our answer. And we're done on those.